It can be used for testing against a variety of possible deviations from independence, including linear dependence, nonlinear dependence, or chaos. The null hypothesis checks for the linearity of data. As the p-value comes out to be lesser than 0.05 for daily, weekly, and monthly data, it indicates that the chosen data is not linear in nature. Next, we move on to plotting a series of box plots to detect outliers. The outliers come out to be a minimum for monthly global active power, which is indicative of using SARIMA for monthly data and LSTMs for daily and weekly.
Now we come to prediction. We've used regression models in prediction. The stationarity of data was initially verified using the Dickey-Fuller test, as that is a prerequisite for regression. We use the seasonal ARIMA model as it is capable of using seasonality to model data. We sample data into daily, weekly, and monthly, and we model this using seasonal ARIMA. The optimum order for daily and weekly and monthly is as shown. Now we come to the results of the model. The performance of the model improved as the sampling frequency is reduced. Now for the interval monthly, you can see the IC value is much less compared to the IC value in the sampling interval of daily. Because regression models were incapable of modeling this data very well, we ended up using a hybrid model that uses LSTMs to model the residuals. Now this helps us predict what the residual could be and makes the ARIMA model more accurate.
Next, we move on to LSTMs. Long short-term memory is a type of recurrent neural network that can learn the order dependence between items in a sequence. LSTMs have the promise of being able to learn the context required to make predictions in time series forecasting problems rather than having this context pre-specified and fixed. This is accomplished by remembering its input due to an internal memory, which makes it perfectly suitable for machine learning problems that involve sequential data. LSTMs are chosen in particular as the problematic issues of vanishing gradients are solved by keeping the gradients steep enough and therefore the training relatively short and the accuracy high. In applied machine learning, we split our data into a train and test set. The training set is used to prepare the model and the test set is used to evaluate it. We generally use k-fold cross-validation that repeats this process systematically by splitting the data into k groups, each given a chance to be held out in a model. These methods cannot be directly used for time series data. This is because they assume that there is no relationship between the observations, that each observation is independent. However, this is not true for time series data, where the time dimension of observations means that we cannot randomly split them into groups. Instead, we must split data up and respect the temporal order in which values were observed. This is done by using walk-forward validation. This walk-forward validation consists of four steps. We start at the beginning of the time series and record the minimum number of samples in the window that is used to train the model. The model makes a prediction for the next time step. The prediction is stored or evaluated against a known value. The window is expanded to include the known value and the process is repeated. That is, we go back to this step one. Because this methodology involves moving along the time series one step at a time, it is often called walk-forward testing or walk-forward validation. Additionally, since a sliding or an expanding window is used to train the model, it is also referred to as rolling forecast. The test results come out as shown. Two different variants of the LSTM model had been chosen, a simple vanilla LSTM model and a CNN encoder-decoder LSTM. The encoder-decoder architecture uses two separate LSTMs, the encoder to read and encode the input sequence, and the decoder that will read the encoded input sequence and make a one-step prediction for each element in the output. The important difference is that an LSTM model is used in the decoder, allowing it to both know what was predicted for the prior day in the sequence and accumulate internal state while outputting the sequence. A CNN is used as the encoder in the CNN LSTM architecture. The CNN does not directly support sequence input. Instead, a 1D CNN is capable of reading across sequence inputs and automatically learning the salient features. These can then be interpreted by an LSTM decoder as per normal. As SARIMA fails to capture nonlinear residuals, we extract these residuals and feed it into the LSTM. The model values are then added to the predictions of the SARIMA model as the predicted error term. These are the results that we obtained from this hybrid model. As we can see, there is a marginal improvement in the results. This can be made better by fine-tuning the hyperparameters and running the LSTM model for a larger number of epochs.
Now on to clustering. Now, before we start talking about clustering, we need to think about a few things. One is, why cluster time series electricity data at all? Well, the main point is to discover recurring patterns in the time series data. Once these patterns are discovered and they're grouped together, we have a much better understanding of what exactly happens in the data, and we can credit different patterns to different real life phenomena. Now, existing clustering methods include centrality-based clustering, such as k-means, or density-based clustering methods, such as dbScan and optics. Now, the instances of the patterns that we aim to observe and cluster will differ from each other only by a small amount, and the number of slices belonging to a cluster is key to identifying whether an